Hi there and welcome from Ventura, California to today's webinar, Advancements in GNSS+INS Technology and Integration, sponsored by InsideGNSS, Novatel, and Inside Unmanned Systems, and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they discuss concepts and methods to optimize GNSS+INS performance of specific applications and their environmental constraints. You'll also have an opportunity to have your questions answered at midpoint, as well as at the end of the presentation during the Ask the Expert panel session with all three of our panel members. Now, today we've invited you, along with over 450 professionals representing 52 countries, across a variety of industries, and over the next 90 minutes, regardless of your industry segment or your location, we're confident you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher, InsideGNSS and Inside Unmanned Systems, would like to take just a moment to welcome you and introduce Demos Xavier, who will be moderating the main portion of today's webinar. So over to you, Richard.
Thanks so much, Lori. On behalf of Novatel, a hexagon positioning intelligence company, and the InsideGNSS and Inside Unmanned Systems team, I extend a warm welcome to our international audience for today's web seminar. We're delighted you could join us. Our panel of experts will provide a very interesting discussion on advancements in GNSS and inertial navigation systems. We've seen significant reductions in size, weight, and power that deliver continually improving levels of accuracy, availability, and integrity. And our panel will explore the underlying concepts of advanced integration techniques. In a short time, will take us from the theoretical to the very practical. But before we begin, I just want to explain our approach to our webinars. At InsideGNSS, we limit ourselves to the number of webinars that we offer each year in order to allow the time needed for preparations that ensure the very highest quality of content by our panel of experts. And I believe you'll find that today's event provides an excellent example of that approach. Now, I want to turn the webinar over to today's moderator, Demos Xavier. Over the years, Demos has helped develop and moderate numerous InsideGNSS and Inside Unmanned Systems webinar, and he's especially close to today's topic. Demos is a professor of aerospace engineering and mechanics at the University of Minnesota, and his research deals with the design of multi-sensor navigation and attitude determination systems for aerospace vehicles. Recently, his work has focused on multi-sensor solutions for operations in GNSS stressed and GNSS denied environments, including the use of such systems on unmanned vehicles. Demos, thank you for joining us today for today's event.
Thank you very much, Richard, and welcome everyone. We're glad that you could join us today for this webinar. And we have a lineup of experts that will present some interesting things about integration of INS and GNSS. Before we start, though, let's do a quick poll. Lori, if you could bring up a poll so to break the ice.
Absolutely, and folks coming up on your screen, you should see that first poll. And we'd like to hear from you. What does having a better quality IMU improve in INS GNSS integrated systems? And in this case, you're welcome to select all that apply. All right, looks like 71% being our front runner with accuracy, 65 continuity, 63 integrity, 49 availability. Demos, any thoughts on these results?
Interesting spread, and I guess as we go through the webinar, you're going to get to see that actually all of these can be impacted in one way or another by INS. All right, so without further ado, let me introduce our first panelist today, and that is Dr. Andrei Solofiev, who is a principal at QNAV. Previously, he served as a research faculty at the University of Florida and as a senior research engineer at the Ohio University Avionics Engineering Center. He holds a Bachelor's of Science and Master of Science degrees in Applied Mathematics and Physics from the Moscow Institute of Physics and Technology and a PhD in Electrical Engineering from Ohio University. His research interests focus on all aspects of GNSS signal processing and estimation, as well as multi-sensor fusion for navigation applications. He is the recipient of the ION Early Achievement Award and the RTCA William E. Jackson Award. Andre, I will let you take it from here.
All right. Well, thank you, Demos. And I'll be talking about some major trends in the GNSS inertial integration and illustrate the application of those trends for a specific implementation example, which is an integration of consumer-grade inertial systems with GNSS. So over the last few years, we're really experiencing quite a bit of a move from more traditional implementation of integrated GNSS inertial systems based on ring laser gyros and fiber optic gyros technology into the use of more and more less costly and less, swap enhanced inertial sensors based on MEMS technology. And MEMS technology covers pretty much fairly large spectrum of, inertial sensor specifications, almost all the way to the tactical grade of the spectrum to very low cost consumer grade inertial sensors that you can put in your cell phone or use for automotive applications. And the quality of MEMS sensors improved quite significantly over the last few years. That makes it possible to consider application of integrated GNSS inertial for a variety of GNSS degraded and GNSS denied environments, such as urban canyons, parking garages, and tunnels. And we'll provide quite a few examples of the performance of the integrated GNSS inertial in this degraded and denied environments through the course of this webinar today. So the main challenge is still the mitigation of inertial error drift. As I just said a few minutes ago, performance of the MEMS inertial improved quite a bit, but we still have to deal with the drift, which is fairly significant, especially as compared to navigation grade and tactical grade inertial units. So how do we address that challenge? Well, with advanced integration techniques, and I'll talk about those in a few seconds, and integration with other sensors as well. So in terms of advanced integration techniques, well, there are three main integration techniques for the integration of GNSS and inertial: loose coupling, tight coupling, and deep integration. And loose coupling really integration at the solution level, where we integrate in GNSS position with inertial navigation outputs. And to me, it has fairly limited benefits, especially when we're looking at the GNSS degraded environments, such as an example on this slide here, where we're trying to navigate in an urban canyon type of scenario. In this case, only very sparse GNSS fixes can be available, and this results in extended number of GNSS outages as well as their duration. So we really have to go and consider more advanced coupling techniques such as tight coupling, integration at the measurement level, which obviously provides us more measurements, even though sparse measurements maybe, but it provides at least partial updates to mitigate inertial drift. And also deep integration, which is integration at the signal processing level, where the inertial is really used to improve the robustness of the GPS signal processing component to recover weak signals, suppress interference, and mitigate multipath errors as well. And integration with other sensors has been used quite extensively as well to improve performance of the GNSS+INS, because as we'll see in a few slides, that performance can be still fairly limited even when we use fairly advanced integration techniques for combining GNSS and inertial data. Some examples of integration with other sensors: integration with video cameras is one example. It's a pretty popular approach due to the low cost of video cameras, and use of motion models, non-holonomic motion constraints for automotive applications as well. I'll give some examples how it works, and Ryan will give some examples as well. In terms of the usefulness of motion models and non-holonomic motion constraints for improved performance of the integrated GNSS inertial systems. So the integration example I'd like to focus for the remainder of my part of the presentation is the integration of GNSS with consumer-grade IMUs. And here we're really talking about the very low-cost sensors at a few dollar price range. Sensors that used in cell phone applications and automotive applications. And the key challenge is obviously we're dealing with fairly large sensor errors. In some cases, the specs are only partially defined or completely undefined. For example, axis misalignments are not always specified for very low-cost inertial sensors. And we have to deal with nonlinearities. For example, heading drift can be a problem due to observability issues and due to fairly large drift of the heading error in a short period of time. So the Kalman filtering techniques, extended Kalman filters, may not necessarily be sufficient for this type of sensors, consumer-grade inertial sensors. However, the good news are that bias and drift themselves for consumer-grade sensors can be fairly large. We're talking about the gyro drift maybe at the level of 5 degrees per second. But this drift and biases, they're fairly stable over a long period of time, and the noise performance has improved significantly as well. So if we're able to calibrate inertial accelerometer biases and gyro drifts, we can use those calibrated values for a relatively long period of time to improve performance of the inertial navigation during GNSS signal outages, or to aid the GNSS signal processing for recovery of weak signals, for example. So in order to integrate consumer-grade inertial sensors with GNSS in the most efficient manner, it's really beneficial to use precise GNSS measurements of the GNSS carrier signal component. Traditionally, integration techniques, tight coupling focuses on the use of pseudo ranges, but it's really beneficial to use Doppler frequency and even more so GNSS carrier phase for the integration, especially beneficial for the integration with low-grade inertial sensors due to the very low noise level in the carrier phase measurements. So we're talking noise level at the centimeter or even sub-centimeter level versus meter level noise in pseudo ranges. All right, so just a few details. How do we integrate GNSS carrier phase with consumer-grade inertial sensors? Well, the good news are we don't have to rely on differential GNSS to utilize precision of the carrier phase for the inertial integration. And we don't really have to resolve integer ambiguities either, because resolving integer ambiguities can be fairly challenging, especially when we're talking about GNSS compromised environments with very few satellites. So how do we approach that? So we have a carrier phase measurements, and there's an ambiguity term in there, but this ambiguity term is constant over time. So what we do is we difference carrier phase measurements over time, over, for example, consecutive measurement epochs for the carrier phase. And the ambiguity term gets eliminated. So what's left here is the temporal change in the range between the receiver and the satellite. And this temporal change in the range is directly related to the change in the position, so we'll lose the sensitivity of the carrier phase observation to the absolute position component. But that's not really a problem because inertial navigation system is a dead reckoning by nature, and it doesn't really sense the position to start with. So we can still observe all the inertial error components, all the traditional inertial error components from the observation of that change in the position, which is again estimated at a very high level of precision because we're using the carrier phase to do so. An example inertial error model, just an example, by no means this is the model to be used for the integration with consumer-grade inertial, but this is a 24-state model with position error states, 3 states, delta position error states, 3 states. This is an additional component as compared to more classical inertial error models to accommodate that change in the carrier phase that we're using for utilizing precision in carrier phase measurements without resolving integer ambiguities. Velocity errors, attitude errors, gyro and accelerometer biases, and axis misalignment, 6 states for those. So 24 states total as an example inertial error model. Also, the good news is for the integration with consumer grade sensors, the strap down inertial mechanization can be simplified quite a bit. due to the fact that we don't really need to compensate for non-inertial effects, such as Coriolis acceleration, centripetal acceleration, and earth rotation. Compensation for those effects can be fairly involved mathematically, and it's not always straightforward and easy to understand and implement, but those effects are way below the noise and sensor errors for consumer grade IMUs. So we don't really have to worry about them. And as a result, the strap down mechanization gets simplified quite a bit. So when we integrate GNSS with consumer grade inertial using carry phase and tight coupling, it improves performance of the GNSS only solution substantially in terms of continuity. We now gain the continuous trajectory through the entire urban canyon. This is an example of downtown San Francisco test with GNSS and consumer grade inertial, but there are still some problem areas, as this example here in the right hand plot, where deep in the urban canyon, we have position errors on the order of tens of meters, which can be quite unacceptable for some of the application scenarios, such as self-driving cars, for example. So we really need to think about augmentation of GNSS inertial integration with other sensors and sources of navigation information. Velocity constraints that I mentioned previously and integration with other sensors, that's the way to go to improve the performance of GNSS inertial for this type of application scenarios. For integration with other sensors, there's quite a bit of sensors in modern cars that are not necessarily there for navigation purposes, but they can be used fairly efficiently to improve performance of GNSS inertial systems. Wheel speed sensor is one example, video cameras is another example. And this is where it gets us when we integrate GNSS with inertial and augmenting that integration with other sensors in the motion model. So carry phase GNSS, consumer grade INS motion model, and monocular video camera. Same example, downtown San Francisco in reliable positioning with lane level type of accuracy through the entire duration of the test. Very similar example on this slide, just another test scenario, but very comparable performance as compared to the previous slide, reliable positioning in urban canyon, augmenting GNSS with motion model and monocular video camera. Here's another example, GNSS outage, driving around in the parking garage for over 5 minutes at a different level. Now, GNSS inertial and motion model integration, not even using the video camera, and able to maintain fairly adequate performance based on just consumer grade IMU. And Ryan later on will show how that performance can be improved even further when a more precise inertial measurement unit is used as a part of the integrated implementation. So as I mentioned previously, we have tight coupling and deep integration. So the good news are also that the consumer grade sensors are now actually at the level where they can be used to improve the robustness of the GNSS signal processing itself at the deeply coupling level to enable weak signal recovery and multipass suppression through the use of extended signal accumulation and specifically extended coherent accumulation of GNSS signals. Traditionally, deep integration has been developed for navigation grade and tactical grade IMUs. But again, as I just mentioned, improved performance of really low-cost MEMS IMUs allows us to consider implementation of deeply integrated architectures and systems using very low-cost consumer-grade sensors. And at the high level, the way it works, we're using inertial aiding to aid extended integration of GNSS signals. For example, to extend coherent accumulation interval from traditional unaided receiver 20 millisecond to something like a 1 second or on the order of 1 second coherent accumulation of GNSS signals. And the benefits are, this is the example of on this slide. This is a UAV example scenario, not a ground vehicle anymore. And we're using the PX4 IMU, really consumer grade IMU, pretty much at the same level as the inertial measurement unit we used for the automotive scenario that we considered a few minutes ago. And integrating this IMU in a deeply coupled manner with GPS receiver, in this case, software-defined GPS receiver. So In this case, because of inertial aiding of the GNSS GPS signal processing, we're able to recover and process GPS signals attenuated by 40 dB from open sky conditions and maintain meter or even sub-meter level accuracy while processing GNSS signals attenuated by 40 dB. So it can be used for weak signal recovery, can be used for interference and jamming suppression as well. So this is a major trends and application of those trends for the integration with consumer-grade inertial sensors that I wanted to talk about. And with that, I'll give it back to you, Demos.
All right, thank you, Andre. All right, so our next panelist is going to be David Gaber. David has led the North American marketing and business development efforts at Epson's MEMS sensor product line since 2012, primarily serving the aerospace, automotive, and industrial verticals. Before joining Epson, David served as an applications engineer at Sister & Donner Inertial, where he supported numerous government and commercial programs. San Francisco Bay Area native, David is a Berkeley graduate and currently resides in the Silicon Valley area. David, I will give it to you.
So, Epson being a Japanese company, we actually have the unique position that we are completely vertically integrated. When it comes to our inertial sensors, this includes everything from synthesizing the quartz wafers themselves all the way through testing and calibration of the gyroscopes and accelerometers in our IMU products. The advantages here are that we can control everything. The IC and MCU specifically, the ownership of that gives us the ability to get extremely specific in terms of everything we want to be computed and nothing that we don't. Additionally, by owning all these different silos of the overall product, we can get very aggressive on pricing. Quartz crystal as a medium for inertial sensors is actually fairly fantastic because you have very efficient yielding. You also have a uniform size, shape, and quality. And this is, of course, different than the quartz found in nature. While beautiful and certainly very expensive, it's difficult to actually work with, particularly the inertial sensors coming from them. We call our quartz MEMS sensors QMEMS, and the advantages here, again, the supply is very stable. We are controlling basically from raw material all the way to sensor fabrication. The material itself that we do fabricate is very stable. We can effectively store already produced crystal for 5 to 10 years before you have any recognizable stability changes. The part-to-part variation is also very low. We drive these sensors very hard. These are vibration sensors. Quartz lends itself well to high vibration. You simply don't break it, and you don't lose vibration even after many, many hours. Probably most importantly for inertial sensing, we talk about temperature performance, and quartz actually yields a very stable temperature performance over the entire industrial, military, and even automotive range. More on that temperature stability, certainly compared to other technologies, the performance of quartz crystal gyroscopes and accelerometers tends to be fairly flat. In many cases, we are about 100 times better inherently than silicon MEMS. And again, this would be completely uncompensated over a given operating temperature range. You look at a blown up view of one of our gyro sensors in that left image, since Epson does own and manage every step of fabrication, we of course leverage Quartz for other products within the Epson portfolio, including timing products, real-time clocks, and then our full line of gyroscopes, accelerometers, and IMU products. On the right side, that image is actually one of the autoclaves in Japan that is used to grow the synthetic quartz. One little fun fact here, from start to finish, the process is measured in months. And this is an uninterrupted period where there's relatively high power required to grow this crystal to our specifications. This is an animated view of how this gyro element works. We call this the double T structure. It is a vibratory Coriolis gyroscope. However, the architecture is somewhat novel. On the outer tines, we are driving the gyro in the kilohertz range. And then during rotation, the inner two tines begin to oscillate according to the Coriolis force. What this gives us is two very important things. First, we have differential detection. I'm going to go to the next slide. What that effectively yields is cancellation of spurious noise from vibration or shock in the operating environment, allowing us to perform without any real compensation or isolation to a much higher level than competing technologies. The gyros themselves are actually fairly simple. We are a single element in a vacuum sealed cavity. It's a ceramic package. There's a metal lid, the IC in the belly of the package, if you will, wire bonded in. What is really the secret sauce, if you look at the image to the left, you see that there is something of a 4-point suspension floating that quartz element above the package itself. Jump to the next slide here, you get a slightly better view. This suspension acts as the secondary vibration and shock isolation system. To reiterate, the element itself, being quartz, and of course with the differential pickoff structure, is already fairly decent at rejecting vibration and noise. This suspension structure takes it to the next level and gives us a bit more performance even through rougher conditions. Electronically, again, fairly simple. The gyro itself is an analog output. Being differential, it is amplified as such. And then we do not do any compensation until we get to the final block there. That's the MCU, where we're compensating for temperature, misalignment, and then scale factor, of course. The differences here, the look and feel of the sensing element itself is different, though it does use the same principle of many of the other leading technologies. What you really get from quartz is a significantly higher Q value. The suspension is certainly one of the biggest selling points across all applications, primarily ground-based. And then the detecting structure itself, what we do with that double T element, you actually are detecting and driving in the same plane. With some tuning fork style gyros, you have some cross-axis interference, if you will, that can negatively affect the signal output. And with that, I'm going to hand it back to demos.
All right. Thank you, David. All right. At this point, we'll take a short pause of sorts here and let you ask questions of our panelists. And please, if you have questions, please send them in, and we'll try to get to as many of them as we can in the time we have. All right, so let's see. First question. This one is for you, Andre, and it has to do with the noise levels. How about the noise levels when you do carrier phase difference measurements and integrating it with INS? Can you comment on what the noise levels are and if differencing actually amplifies it?
Sure, that's a great question. Well, the differencing definitely amplifies it. You in the best case you difference two independent random variables, and the sigma goes up by the square root of 2. So that's sort of a disadvantage. However, we're dealing again with very low noise carrier phase measurements to start with, and the noise level is, as I mentioned, centimeter or even sub-centimeter level, maybe even millimeter level. So the fact that we have this very low noise component to start with, the amplification doesn't really hurt us all that much in terms of the ability to estimate inertial error states. And especially when we compare this noise level, we have sub-centimeters multiplied by the square root of 2. We compare it to meter level noise in pseudo ranges, it's still 2 to 3 orders of magnitude lower than that.
All right, thank you, Andre. All right, this next one is going to be for Ryan. I know I have not introduced you yet, but you will be coming on shortly here. And it's on the question of definitions. And the question is there a standard definition of what people call loose, tight, deep, ultra-tight INS GNSS integration?
Yeah, that's definitely a good question. And the answer is no, not really. There's a couple of competing terms. I think loosely coupled is fairly well known, which Andre did a good job of explaining. That's taking the GNSS computed positions only. Tightly generally refers to taking the raw measurements, so the carrier phase and pseudo range that Andre was just talking about. And the difference starts to get between deep and ultra tight. They tend to mean the same thing of feeding the inertial solution back to the signal tracking to aid there. There's some nuances and people use different terms. I like deeply coupled, but even I get caught sometimes saying tightly and ultra tightly. So yeah, you have to read between the lines a little bit to make sure you know what people are talking about.
Okay. Anything you want to add to that, Andre, by any chance?
I agree with that. There's no, when we talk about loose coupling and tight coupling, it's pretty clearly defined what that means. When it comes to the ultra tight versus deep integration, I don't really know what the difference is. Different people may define differently. Personally, I don't really like the term ultra tight. I would just prefer, okay, we have these 3 different integration techniques, because there's no really major differences, conceptually from ultra tight, going from ultra tight to deep. To me, it's integration at the signal processing level, as Ryan just summarized essentially. And I think preferably just use 3, but historically we used all 4, and I guess we'll just gotta live with it.
All right, well, the confusion continues. All right, next one. This one is for you, David. Is about interpreting numbers on inertial IMU spec sheets. How does one interpret those? So they should interpret them as the worst case performance numbers, best case performance numbers, somewhere in between. Anything you want to say about that?
This is a good question. In fact, from the supplier side to myself, and I'm sure as Ryan could say as the GNSS integrator, specmanship is one of the worst parts about this industry. The variation from supplier to supplier in terms of how they define parameters, that is one issue, but the second issue is some make it very clear there is a min, a nominal, and a max value for each parameter, and some just specify one with a statistical caveat. I would say that the higher performance IMUs, the fiber optic, the ring laser, and even some tactical grade MEMS, the specmanship is better. You are certainly very clearly representing whether the nominal value is what is specified or if there is really a min-max. In the case of Epson being a Japanese company, we are very rigid in the way that we specify. And generally, we just put a nominal, but we will qualify it in the notes or the footnotes exactly how it was derived and what the end user can expect of sample variation from that. So I haven't answered your question at all, but other than to say it really depends vendor to vendor. And if you are shopping around, I would encourage you to ask the tough questions of the supplier, because their answer and the way they give the answer will tell you more than the spec itself.
Oh, thank you, David. No, actually, I mean, that's the key thing. It depends, right? So I think that's a good thing to know. All right, let's probably do one more question before we continue on. And this one, I'll direct it at you, Andre. And it's a question about, have you considered PPP techniques with INS GNSS processing? Given the convergence issues, what would you expect the accuracy to be?
Okay, well, for PPP, the precise point positioning, convergence, I'm not really an expert in the precise point position, but the way I understand, convergence really relates to your position solution. So when we're dealing with, integration at the measurement level, that convergence doesn't really matter in a sense, but the question may be like, do we consider the use of, corrections that are applied in the PPP case, such as precise ephemeris products? And to me, you can use those, but I haven't personally, we looked at the use of differential GPS for, the carry phase-based integration with inertial, and I personally haven't really see much of a difference in that case, especially for consumer-grade INS. The difference in, what's the benefit of, being able to eliminate iono, tropo, and ephemeris errors, and is there a benefit for the quality of the inertial integration? Not that much from my experience. Ironically, again, we're not talking about the position solution. We're just talking about the ability to calibrate inertial error states, and mostly focused on low-cost inertials. So to me, there's not that much of a difference, standalone carry phase versus PPP type of correction techniques, or even differential correction techniques.
All right. Thank you, Andre. Ryan, do you want to chime in a little bit there?
Yeah, I agree with what Andre said, but if you're talking about INS and PPP, the angle to look at it might be the feedback that INS can provide to PPP, because one of the issues is convergence. And if you have a short outage of your PPP corrections, then you can use your inertial solution to reconverge more quickly. So the advantage isn't necessarily PPP helping INS, it's kind of the opposite.
Okay.
Yeah, that's an excellent point, yeah.
Excellent. All right, let's move forward, and we're going to have a second Q&A session at the end here, so keep the questions coming. And let's see, so before we do that, let's go to a quick poll here. Lori?
All right. Second poll of the day, and love to hear from each of you. When considering the purchase of an INS solution, how important is the quality of the IMU in your decision? Very important, somewhat important, not important, or not sure. Looks like majority here, 42% saying very important, 40% important, 30% coming, or 13%, sorry, coming in with somewhat important, 2% saying not important, and 4% not sure. So Demos, any thoughts on these results?
Well, for those that marked not sure, the next two presentations will help, I guess, clarify the importance or lack thereof of the correct IMU. So with that, let's give the, I guess, the presentation back to David, who's going to talk a little bit more about IMUs again. And David?
Thank you very much. When it comes to IMUs, and certainly as referenced by several of the questions I've seen pop up here, noise is the big question. And again, what you will notice that you're paying more for less, essentially. In the case of Epson, if you look at the two plots on the bottom there, what you have is all three axes of one of the Epson IMUs overlaid, and the same for some leading silicon MEMS. The vibration profile is displayed up top in black. Effectively here, we're just demonstrating the vibration resilience of the two different IMUs. The quartz crystal is a big help. The suspension system certainly gives us a little bit of an edge there. I'll talk a little bit further about some of the other mechanics that are employed here, but the ability to output a usable signal during high vibration events, certainly for land vehicles, is quite critical. The same can be said for shock. Same setup here. Shock has always been, at least historically for automotive, passive and active safety. These are two events where you can have somewhat devastating effects if you have a false positive. Epson has been involved with airbag deployment systems for many years, and believe it or not, one of the biggest problems is a pebble on the highway strikes the bottom of the vehicle, or a bump is hit at a certain angle. If the shock is detected at the magnitude for which the system is programmed to blow the airbags, you effectively have a totaled car interior for no real reason. So the ability to deliver that clean, usable signal through high shock events, also critical. Performance over temperature, certainly for longer term positioning, extremely important. What we have shown here on the left side, the black and orange is the same Epson IMU. However, one is uncompensated and the other is compensated. What you'll notice, even without compensation, you still have a fairly flat bias over temperature. And this is, again, fundamentally the quartz offers a much more stable temperature profile than some other technologies. Noise itself, when we talk about Epson in the analog and digital, again, the analog is just the raw output directly from each sensor. In the digital domain, this is when the compensation has clicked in. The noise, because the quartz is a piezo pickoff versus capacitive in other technologies, you tend to get roughly 10 to 100 times better signal to noise ratio. When we talk about evolution of products here, I mentioned the automotive safety systems. Back in the early 2000s, Epson had really established a foothold in both DSLR lens stabilization and automotive dead reckoning. This was when you had a single axis gyro on the Z-axis, giving you very coarse compass feedback for primitive navigation systems. From that point, we got into the multi-axis and then eventually into a full IMU type product. The IMU product has evolved over the years, and now we offer our flagship, the G3 series. I'm going to go into a little more depth there. Also at the tail end, you have the G450. I'll elaborate on that in coming slides. I think the key message here really is the entire industry is evolving so rapidly. The MEMS IMUs have leapt forward in performance they can achieve, the amount of power they draw, and of course, size and weight. Speaking of performance, the silicon MEMS, and then of course, Epson being quartz MEMS, there is a lot of overlap, particularly on the lower end of performance, but as we get closer to tactical grade, these are areas certainly dominated by fiber optic and ring laser. The MEMS IMUs are creeping down. You have leaders both domestically and internationally. Sub 1 degree per hour in-run bias stability is now standard. It's a reality. And I can remember not even 5 years ago that seemed impossible. So it is amazing to watch these technologies just launch forward. Our flagship product, based on what we call the G3 series, this is just one variant. Very compact package, roughly the size of a starburst, weighs about 2 starbursts, but you actually have a host of fairly advanced features, particularly for integration with GNSS. The connector itself, this is our 3rd generation connector, has received very positive feedback even in the worst environments. The external housing itself is metal. We have a grounding area integrated right onto the housing itself. The black core, this is probably the largest amount of Epson IP, and it is very much a black box, quote unquote. It is actually mechanically isolated from the external package using all kinds of different proprietary means. That is the 3rd pillar of the Epson isolation. We call it triumvirate. Again, you had the quartz element itself, you had the suspension structure, and then you complete that with a ring isolation type system for the entire sensor cluster. Looking back and then looking ahead just a bit, this is a chart of the current Epson IMU offerings, and you see as you push to the right, the performance increases. This level of performance is now become an industry standard for MEMS in general, certainly the higher end MEMS, and there are many options to choose from with varying technologies that get darn close to the tactical grade where fiber optic lives today. Heading into the future, Epson, we are pursuing 2 different strategies. There is a realization that at some point we will have to make the element bigger or completely redesign it to continue pushing performance down. However, the market's tolerance for a larger, heavier, more power-hungry IMU is questionable. In fact, in my opinion, I would say most people would reject that. So Epson is taking a different strategy to drive down performance, and that is multi-sensor integration. This is a technique that is used in different ways by many other vendors, but you're effectively adding multiple sensors per axis and using some fairly robust computing to drive down noise and drift. And with that, I will hand it back to Demos.
Thank you, David. All right, so our final panelist is Ryan Dixon, and Ryan is a chief engineer of the Novatel Synchronized Position Attitude Navigation SPAN GNSS products group. His responsibility includes enhancement of Novatel's sensor fusion technology and overseeing the long-term direction of the product line. Ryan joined Novatel in 2005 after completing a Bachelor of Science degree in Geomatics Engineering from the University of Calgary. He moved into the SPAN development group in 2008, where he became a technical lead in 2010 and a chief engineer of the group in 2013. His knowledge and experience in integrated inertial measurement technology from navigation grade to commercial MEMS systems with GNSS technologies has developed a wide range of augmented positioning solutions for both ends of the cost and performance spectrum. Ryan, the floor is yours.
All right, thank you very much. Yeah, so I'm going to try and put together the pieces of the earlier presentations here and talk about what constraints and inertial algorithms can get you with a good MEMS IMU, and what can be done without getting to the aiding sensors. Right. So, yeah, so SPAN is Novatel's GNSS+INS product line, and it's been on the market now for about 15 years, and we use the deep coupled architecture, or ultra tightly if you prefer, which we, I guess, don't. So basically that means that we are feeding back to the signal tracking loops and using the partial GNSS measurements as well. Over those 15 years, SPAN has gone from using the ring laser gyro quartz accelerometer technology to MEMS as it's really accelerated. And one of the things I really like is that all of the time plots from all the presentations show the MEMS really starting to explode in the last 5 or 6 years, which we've really seen as well. So we've been kind of trying to be at the leading edge of performance to cost and size throughout time. And for sure, it's getting more and more difficult to do as the MEMS get better very quickly. So if you kind of look over history there, the piece that SPAN helps with and inertial helps with is urban canyons and things like that. So this is a picture I really like of what GNSS alone will do in an urban canyon versus what the inertial engine will do. So as Andre kind of talked about, this is what a deeply coupled system will do in an urban canyon. And the piece I want to talk about today specifically is what we call land vehicle technology. And this is adding constraints to standard technology. In this case, we'll be talking about constraints for a fixed wheel land vehicle. And it's the non-holonomic constraints essentially. So we're trying to gain additional performance for things like vehicles in tunnels, for mining equipment, agricultural equipment, in fields or in pit mines. There's military applications as well to really improve the robustness of the positioning and the accuracy of the positioning in as many cases as we can. Now, there are 3 kind of big tenets to this land vehicle technology improvement. The first is vehicle velocity constraints. They're essentially what Andre was talking about before as non-holonomic constraints. It can colloquially be called dead reckoning as well as really how you're going to do positioning without GNSS for a long time. So these constraints help all the time, but they really help when GNSS is either partially denied or totally denied. So tunnels, urban canyons, forests, all that sort of stuff. The second is phase windup relative attitude updates, or Azimuth really. And the idea here is that because GNSS uses circularly polarized signals, that we're actually able to measure the antenna turn or the wind up and down of that signal as you turn. And by doing that, you can use those as updates to the inertial filter to try and get your bias estimates updated for the vertical gyro mostly. And that really helps in low motion environments, because in low motion environments, you don't have very much to measure. So anything you can do helps quite a bit. And the third doesn't really show up in the performance plots, but its goal is to improve kinematic alignments. This is something, if you had a dual antenna system, wouldn't be as big of an issue because you could take your initial attitude from that. But if you have a single system, you need to take your initial azimuth from somewhere. And the way to do that is your GNSS course over ground. Historically, it's not been as big of an issue because mobile mappers and things follow procedures and know they can align forwards and have to drive a certain speed. But as we get more consumer, it's going to be a bigger and bigger issue. And one scenario I like to think of, it reminds me of Austin Powers when he's driving back and forth in the tunnel. But basically, if you're this car here in the middle and you're trying to do a 30-point turn out of there, your GNSS course over ground is going to be pretty inaccurate because you're moving slowly, and it's also going to be sign flipping every time you go into forward and reverse. And something you need to just kind of have happen automatically is to detect which way you're going and inject an azimuth only when you're certain. Because if you inject a bad azimuth, you can be in trouble for an inertial system. So given those, I've got 3 test cases to look at here. The first one is urban canyons to see what these constraints can add in that case. The second is low dynamics, so that's simulating the bigger type of vehicle, like a mining vehicle or agricultural vehicle. And the third is an extended GNSS outage, so that's doing the dead reckoning constraints over time. And these tests are using GNSS and an IMU only, so no aiding sensors were used. They definitely help, but we're trying to show what can be done before adding extra help. So the equipment used here was the Novatel's PowerPack 7 E1 with the Epson G320 IMU inside. I've grabbed the spec sheet here. I won't go through it too much in effort of time, and David had better full complete specs for the G320 as well. The first test case is an urban canyon, so we use downtown Calgary because that's Novatel's headquarters. In this kind of scenario, we expect the benefits largely from the deeply coupled, see, I've done it again, tightly coupled architecture, so the use of partial GNSS information. But we expect the land vehicle technology constraints to help during the most difficult periods. And one example in Calgary here I've pulled up is kind of a coupling between buildings that's between 2 malls. So it's a place you creep through because there's a pedestrian underpass there that you can creep through there pretty slow, which is a pretty difficult scenario with lots of reflected signals and things like that. Now, if I look at the error plots here, so in red we have the standard inertial mode, and in green we have the inertial constraints. Now you can see that for most of it, they're pretty much the same, but there are a couple areas where you can clearly see that the constraints have done something to the solution. And there can be a couple reasons that that you drift a little bit in downtown, multipath reflected signals, or inertial drift when you sit under a blockage like I showed in the picture above. So the one in the middle there, the biggest one, is that it's a reflected signal that could get in. And you can see when we activate the constraints, we're able to more accurately reject that signal and feed better information into the tracking loops, so that doesn't happen. And then bridge through until we get the next position update and everything matches again a little bit later. If we look at the azimuth domain, we're able to constrain there as well. So in this case, the pink is the standard mode and the blue is the land vehicle mode. And you can see in sort of the same GNSS times here, we're getting a little bit of error constraint as well. So we're able to pull that in a little bit. And this would matter if the application was something to do with LiDAR or photos where you needed to use the attitude to relay whatever your sensor was observing, or if you say you were going to go into a tunnel during any of these times. The closer your azimuth is going into an outage, the better you're going to be able to bridge an extended outage to a tunnel or something. So that's it for urban canyon. And the next test case we'll look at is low dynamics. So in this case, we did a 2-kilometer straightaway back and forth on this rural road, trying to simulate mining equipment or agricultural equipment. And in this case, we have ideal GNSS conditions, so that's not the problem. But the problem is we have difficult INS conditions. And what I mean by that is we have limited observable motion. So you're trundling along at a low speed and a consistent speed. It's actually really hard to measure much from your IMU. Which means it's hard to separate your biases and your changing noise and things like that from motion. And what the vehicle motion constraints and phase windup attitude updates are going to do is provide that observability. I'm not going to look at position plots in this case because with good GNSS, you're going to be as accurate as your GNSS positioning mode would be. But we're going to look at this azimuth again. And the same colors apply. And you can see the effect of the land vehicle technologies boosted a little bit. So we're able to constrain the peaks of those azimuth errors quite a bit more on long, slow durations where naturally you're going to get larger azimuth errors. And that would help in the same type of scenario. So if you were in a mine and you came up to the pit mine wall, or if you were using LiDAR photos or something and you needed that attitude, that's really going to help a lot. And the third scenario is the extended outage. So we did a parking garage as well. This is the parking garage at the Calgary International Airport. And we spent about 10 minutes there. I know this picture on the right looks like we're driving on the surface, but we're down and went up and down these helix ramps as well, because that gives a nice height change, which makes it a little bit harder to constrain things. So in this scenario, performance is going to be driven by the IMU quality and by the inertial algorithms and constraints that you're able to apply. And it's really pretty clear in a position plot. Red again is the standard mode and green is the enhanced land vehicle mode, that in the standard mode, you get the second order error growth you would expect. If you recall Andre's plots, he showed the 2 integrations of acceleration to get to position. And that's basically what you're seeing is errors integrated twice. And the constraints are going to remove as much of that error as you can. So you can see in the green line, we've bounded it way, way lower than you would get with a standard mode. And you can look at this in the velocity domain as well. So now you're doing 1 integration to get to velocity. And you can see the red line is more or less a linear growth, which you would expect. And the bounding happens in the velocity domain as well. And I like to look at this, you know, on a map as well. So the center and left images there are standard modes with 2 generations of GNSS card. They're pretty similar. The helix runs were done at the end, so that's where you see the greatest error growth of kind of spiraling off the helix there. And the right image is when we turn on the constraints and we're able to really pull that error in quite a bit. And this was about a 10-minute outage or so. The last thing I want to touch on is outages longer than that. There's an error statistic called error over distance traveled that people may have heard of. There's a lot going on this plot, so I'll kind of back this up a little bit. But I'm trying to explain error over distance traveled. So if we look at the left-hand column only, this is the error we get over an hour with land profile on, and the percentages there are the percent over distance traveled. Now, inertial errors grow over time and not over distance. So this metric you may see, but it doesn't really mean that much, because you could drive further and have a larger denominator and your error would be lower, or you could drive slowly and it would look really bad. So we've done simulated outages over lots of different conditions and different distances to try and give a statistical meaning. So that's what these are. The light colored area is the 1 sigma variance on the average, and then the dotted lines are the average. The different classes here, S1 IMUs are our MEMS IMU family. The S2 is tactical grade, and the S3 is sort of the near navigation grade. So if you look from the blue one there at the top left, you get pretty good distance or error over distance traveled. But the shorter that outage is, the more variance you get on that. And that's because you have shorter distances traveled and a lot of the initial error happens at the start. As you increase your IMU grade, that variance goes down quite a bit, as well as the overall percent of distance traveled. And then if we look at the right column, this is the one sort of nod I have to adding sensors. So in this case, it's an odometer or a DMI. And you can see that it reduces the overall error a little bit, but it really also reduces that variance early on. So the real meaning I wanted to portray here is if you see error over distance traveled metrics, kind of like the spec sheet question David answered earlier, is be careful what it means and what scenario it was tested in, and ask questions. Yeah, so that's about it. So overall, can get really remarkable performance now from MEMS IMUs. But if you're selecting a system, be really careful about what your desired environments and metrics are, and you can kind of choose accordingly. It's not an easy selection to make. I think that's it, so I'll hand it back to you, Demos.
Thank you, Ryan. All right, so before we head off to our final Q&A session, a couple of things that we want to do. One, let's do a quick poll. And Lori, if you could bring that poll up.
Absolutely. Third and final poll for today. In what harsh GNSS environments do you struggle to provide high accuracy positioning? So I've got some choices there: urban canyons and/or foliage, jammed, spoofed indoors, or kind of tunnel underground's pipeline. Looks like 70% saying urban canyons and/or foliage, with 34% jammed, 26% saying spoofed, 42% indoors, and then 55% tunnels underground and pipeline. What do you think about those results, Demos?
It looks like a nice spread of different types of users and applications in the audience today. All right, so let's see. Let's move on. And so on this slide, you'll see, if you're interested in learning more about what our panelists talked about, here will be a link and it will also be coming through the chat, so you could go there and take a look at this paper, or take a look at those links to learn more about the subject matter that was talked about today. All right, and so with that, let's head on to our final Q&A session. And a lot of questions coming in, keep them coming, and we'll try to address as many of them as we can. This first one is for you, David, and it's a question about the Epson products. It's how do you differentiate, or do you differentiate the application scenarios such as UAV and ground? And if so, do you regard Epson products as MEMS or something else?
Yeah, so as far as the differentiation goes from application to application, Epson strategically some years ago made the decision that our role was delivering the best IMU only that we can. And when we talk about ground-based versus UAS, the parameters that we change are things like dynamic range, bandwidth, even some of the synchronization features that we unlock for GNSS integration. I would say on the UAS side, for anything short of a Predator or one of the larger drones, the autopilots from leading vendors today really seem to be good enough. There is a limit to what those can do, obviously, but we do not have a specific product that we recommend for UAS. It really comes down to the needs of range. Second part of that question here, we do regard ourselves as MEMS, though it's using a quartz medium versus silicon. We still incorporate a etching process. Photolithography is used extensively, and it is a moving gyroscopic and acceleration sensor. It just happens to have a much larger form factor than most silicon MEMS sensors.
All right, thank you, David. Next question. This one is going to be for Ryan, and it's a question about, can you say something about SBAS and whether SBAS services were used in any of the results you presented, with the Calgary tests?
Sure, yeah. SBAS was not used in any of the tests I presented today. We just did single point standalone positioning, but they certainly can be, and they are in general tests we do, as well as PPP and RTK modes.
Right. Let's see, next one. This one is for you, Andre, and it's a question about a comment you made I guess in your slides, that you did not specifically consider the Coriolis effect. And the question is, isn't this the drift going to increase further without this compensation, and why was it justified to ignore?
Okay, so basically, as I mentioned during the presentation, the Coriolis effect, as well as other non-inertial effects related to the fact that we navigate in the non-inertial frame, they are, way lower as compared to inertial sensor errors. The Coriolis effect is really, non-zero velocity in a rotating frame, which is, Earth-related frame, where we're interested to provide navigation outputs. So it's the velocity multiplied, in some form by the Earth rate, and it's pretty small. So this is an acceleration component that we're ignoring. And I can't remember the numbers, from the top of my head. And obviously, because it's related to the velocity, it depends on the velocity. But for the majority of the applications, unless we really go into, very high velocity values, that Coriolis acceleration is pretty small as compared to accelerometer biases. So the fact that we're just ignoring it doesn't really hurt us, because we have bias and as well as accelerometer noise that are, way larger as compared to this Coriolis acceleration.
All right. Ryan, is there anything you want to add to that, or?
No, not really.
Okay.
We still tend to do it, but Andre's right. It's a couple of orders of magnitude below what we can kind of detect, so you don't have to.
Okay. All right. Let's see. Next one. This one is for you, David. It's for the Epson vibration testing. Are the results shown, including a third level of isolation, or will this further improve performance? Let's see. Okay, the results shown include a third level of isolation, the closure, or will this further improve performance under high vibration?
The charts that I showed did not reflect closure. This was gyros removed, simply the gyros in their own housing, so you had the benefits of the quartz and the suspension only.
All right. All right, let's see, next question. Let's see, this one is for you, Ryan, is what extent or duration would the system go before, I guess he's talking about SPAN, requiring GNSS observations to correct the INSS part of SPAN?
Yeah, okay, I'll give the answer that nobody likes, is that it depends. So I'll assume if you're talking about normal mode, so you get basically a second order error growth, will propagate basically indefinitely, but your error will become unacceptable to whatever application at some point fairly quickly. If you use constraints, you're able to extend that quite a bit. So there's not a point where we'll cut it off really and say you're done until we get, till we're pretty sure we're not on Earth anymore or something like that. But yeah, you got to kind of watch the estimated variance output and know what your limits are, and that's really the answer, I guess.
All right, thanks. Question for you, Andre. With respect to consumer level IMUs, what is a good practice to address the turns on accelerometer and gyro biases? Again, I take it has to do with the results that you showed in your slides at the beginning.
Oh, you mean the turn on biases?
Biases, exactly. Sorry.
Okay. All right. So with gyro biases, again, like as I mentioned during the presentation, the biases themselves can be fairly large. So accelerometer biases sort of maybe, a meter per second, even 2 meters per second squared. And the gyro biases can be, 5 degrees per second. Pretty large, but pretty stable. The gyro biases can be handled pretty easily, actually. You just got to detect when the vehicle is stationary and use stationary data to estimate gyro biases or gyro drifts, whatever you call them. And ignore the Earth rate because, again, this is way lower as compared to the drifts. Accelerometer biases, because they coupled with the gravity and the tilt errors, you really have to exercise some, turns and maneuvers, start moving and use carry phase measurements, or if carry phase not necessarily going to be available from some receivers, at least the Doppler to calibrate those out.
Right. Thank you, Andre. Let's see. This one is for you, David. Can you say something general about, I guess, cost performance of the QMEMS compared to silicon MEMS?
Yes, I would say the cost is actually very similar. As you get lower and lower biases, let's take Epson's latest G370, that's a 0.8 degree per hour. That level of performance you can find with silicon MEMS as well. What really drives the cost is how integrated the supplier really is. And in the case of silicon MEMS, you have several who are completely integrated and they own everything from fabbing the sensors to testing, just like Epson. Where you start to see some, what I would say, real differences in pricing is when you get to the more exotic sensors, and this exists both in quartz and silicon. These tend to be lower volume producers, and they tend to also be lower yield. They pursue very advanced, very complex sensing structures where repeatable performance is not always possible, and that will drive the cost up. However, I've seen those get 10 times better than anything we can do, and I believe they can probably get even lower.
All right, thanks. Let's see. All right, so this next question is for you, Ryan. And it's what are the key challenges in tightly coupled GNSS/INS integration for centimeter level of accuracy?
Okay. Yeah, there are a couple. You would think it would just be easier, but that's not necessarily true. The biggest one is probably variances. So RTK solutions have really low variances that can cause filters to become over-optimistic if you're not careful. So you have to be careful about that. And the second big one I would say would be lever arm measurements. So when you're in meter level positioning, your offset lever arm is the offset from the IMU to the antenna. And if that's off by 10 centimeters, it's okay in standalone modes. But once you're in RTK, you can actually start to see those small lever arm variations playing into your solution. So they have to be, measured very, very well.
All right. Andre, would you want to add anything to that, or?
Actually, yes. So to me, another challenge is, when you're looking at the RTK at the centimeter level and using something like a lambda method to resolve integer ambiguities, you're really relying on your covariance matrix for your ambiguity states and the cross correlation between those states. So you really want to make sure, your cross correlation is, agrees closely to the real correlation between the errors, because if it's not, you're not going to resolve your ambiguities right. And there are two challenges, in terms of really making sure that the covariance matrix is the right covariance matrix. It's consistent. One is, GNSS errors, especially in degraded environments. How do you model multipath, things like that. And another one, when you're integrating with low-grade inertial, how do you make sure your inertial error model is consistent and your inertial error covariance is consistent to the actual inertial performance?
Right. Thanks, Andre. This next question, actually, I'll point it at you, Andre, but I'm pretty sure Ryan could also chime in afterwards if he wants to. And it's kind of a general question. It's looking at trends. It says, apart from advances in sensing performance, what trends are there in the algorithms used for INSS GNSS as enabled by increased microprocessor performance? In other words, is there stuff that we could do with, I guess, the powerful microprocessors that are becoming available now?
Right. So I don't really see any specific trends, in algorithms, but there's definitely stuff that we can do with, increased microprocessor performance. Well, first of all, you can use, a larger inertial error model with more states, and that sometimes help to just model, inertial errors. For example, making sure that your covariance is consistent with the actual system performance. That's at the tightly coupled level. Also, you can look at the deeply integrated implementations on a pretty cheap processors. You probably need FPGA for that, not just a microprocessor for the signal processing component. But that's an additional benefit that you can exploit and utilize, integration at the signal processing level, deeply integrated architectures.
Ryan, anything you want to add? Any capabilities you see coming down the pike because computation is becoming easy, affordable?
Yeah, I agree with Andre that for the most part, INS is actually not that limited by processors, or hasn't been for a little while. But I think where that's going to play a big role is when we start talking about additional sensor fusion. So when you start talking about doing more photography integration or LiDAR or things like that, where there's thousands of points or things to deal with, that's really where bigger processors are going to enable more stuff to be done.
All right. Let's see. Okay. Next, this one is for you, David, and maybe kind of an unfair question, and it's almost in the category of why is the sky blue, but why isn't there an agreed upon error model definition for inertial sensors?
We get asked the question all the time about why on our data sheets we can't provide data for error over time in this application, such as undersea vehicle or drift in a highway vehicle. And the reality is, it really depends. When we're talking about Epson's inertial sensors themselves, we tend to, our Allen variance gets us down to about the best point in 32, 33 seconds. And we don't do, in the IMU itself, any real algorithmic computation other than temperature and misalignment. We barely do delta V, delta theta, except on our new products. So when we are modeling temperature, which is probably the most advanced computation we do, we are using a very, I think, standard approach, lookup table, and then a dynamic means to analyze the rate of temperature.
All right. Thanks, David. All right. Let's see. This question is going to be for you, Andre, but Ryan, you could also add in after Andre answers if you like. And the question is, can you comment on the attitude, on the altitude performance in dead reckoning while using MEMS sensors?
Okay. Well, the specific numbers they depend, obviously, on the duration of the GNSS outage and the type of outage, if you're talking about partial or complete outage. But generally speaking, the altitude performance can be pretty good. On one hand, one of the reasons the tilt errors don't project into the vertical, and that helps. But also the non-holonomic motion constraints in the vertical direction can be used fairly efficiently as well. So the altitude performance can be fairly good. Again, like numbers would depend on a specific outage scenario for GNSS.
Ryan, would you want to add anything to that?
Yeah, I completely agree with Andre. It's I don't know how well known it is, but with GNSS, height is usually the worst of the two. But for INS, it's the opposite because we have the good gravity measurements. So yeah, generally we present 2D position errors because they're the harder one. So yeah, usually altitude is better.
All right. Well, unfortunately, it looks like we're running out of time here, and there are a lot more questions. We appreciate for you sending in the questions, but I think we're going to have to wrap it up at this point. So with that, I think I'm going to hand it over to you, Lori, to close the webinar.
Absolutely. Thanks, Demos. And everyone, before we sign off, would certainly like to take a moment to thank each of you for joining us and trust that you found today to be of value. Very special thanks to our distinguished panel members, Andrei Soloviev, David Gaber, and Ryan Dixon, and of course our sponsors, Novatel, and our co-hosts, InsideGNSS and Inside Unmanned Systems. most importantly, again, thanks for joining. This is Lori Dearman saying, hope we see you on the next one. Have a great rest of your day. Bye for now.